Time to begin. How's everyone doing today? Good? Good weekend? Excellent. Cool. Well, today we're just going to dive right into it after some announcements. Don't do it. Don't do it. Okay. So, some announcements. We have a homework due tonight. Thank you. We have homework due tonight. No, she's nice, I promise. Homework due tonight by 11:59 p.m. Okay, exam on Friday. There's a practice exam posted on Canvas. I remembered right before class started, someone wanted me to post a trig review, so I will also do that soon. But make sure you go through that practice exam. If you feel good about all those problems, then you'll probably be good on the exam. Okay. And then office hours are going to be virtual this week. So just Zoom, it's the same Zoom room you use to log on to class. Just use that to come to my office hours if you need any help with anything. Okay. Are there any questions before we get started?
So we don't have any homework this week because of the exam, just to study for it, correct?
Correct, yep. All right. All right, so let's get started. So last time we talked about the chain rule. Okay, probably the most important differentiation rule you're going to learn. It's only a little bit of an exaggeration to say that the rest of the semester is just going to be applications of differentiation and really applications of the chain rule. Towards the end of the semester, we'll get into another fundamentally different topic, but really the rest of the semester is mostly going to be how can we use this thing that we've defined here, the derivative, okay? So as a reminder, the chain rule says, suppose y is a function of u, a differentiable function of u, okay? And u is a differentiable function of x. Okay, then f of g of x is a differentiable function of x, and dy dx, the derivative of y with respect to x, is simply the derivative of y with respect to u times the derivative of u with respect to x. Okay. Another way we write this is f of g of x prime is f prime of g of x, so the derivative of the outside at the inside times the derivative of the inside. Okay. So this is the chain rule. So an example, this one's a little different than the examples I did last week, but it's still the same idea. Suppose y is this function, u to the fourth minus 3 times the sine of u, and u is x cubed plus 1. Then what is dy dx? So before we knew the chain rule, the only way you could try to do this was to plug in u is x cubed plus 1 and get y equals x cubed plus 1 to the fourth minus 3 times the sine of x cubed plus 1 and try and differentiate that before the chain rule, right? Now with the chain rule kind of lets you, especially in this type of problem, lets you do it in reverse. It lets you differentiate first, and then you can plug in what u is. Okay, so we want to find dy dx. Well, by the chain rule, what is this? I have y is a function of u, and u, oops, and u is another function of x. So dy dx is what? Well, we're looking at this line here, right? So what am I going to get here? I don't want anyone to calculate it. Just tell me what I need to start writing. Dy dx is equal to so I want this thing, right? What is that equal to? Literally, I just want you to read what is right there right now. So someone out loud read me that line.
dy over du times du over x.
Yeah, dy du times du dx. Excellent. Oh, was someone in the chat screaming at me? Yes, thank you, Saba. Yeah, the chat doesn't ding at me, so my bad. All right, so dy du. Well, this is just the derivative of y with respect to u, right? So what is that? What's the derivative of y with respect to u here? Yeah, what's the derivative of this function right here with respect to u? So what's the derivative of u to the fourth with respect to u?
4u to the third.
Yeah, 4u cubed. And then what's the derivative of minus 3 times the sine of u with respect to u?
Minus 3 sine u.
Minus 3.
Or cosine u.
Yeah, cosine of u. Very good. So there's dy du. And then what's du dx? Yes, thank you, Saba. What's du dx? 3x squared. Perfect. Excellent. Okay. So this is technically the derivative, all right? But if I ask what is dy dx, what is the derivative of y with respect to x, I want my answer to only be in terms of x. Okay, so at this point, you can plug in u is x cubed plus 1. Okay, so this is 4 times x cubed plus 1 cubed minus 3 times cosine of x cubed plus 1 all times 3x squared. Okay. And notice if you had first plugged in x cubed plus 1 and done the chain rule the other way that we've been doing it, where we discussed what is the outside function, what is the inside function, this is still exactly what you would have gotten, just a slightly different form.
Can you repeat what you did right there, please?
Right here, yeah, so to go from here to here, I plugged in u equals x cubed plus 1 into here and here. Okay. And again, the main reason we do that is if I ask a question in terms of x, you should give me an answer in terms of x, right?
You can leave it like that as an answer.
Yes, you can leave it like this as an answer. Absolutely. You mean the bottom line or the one with the u's in it?
No, the bottom.
Yeah, the bottom line. Yeah, it's perfectly acceptable as an answer. Excellent question. Yeah, so someone says, could we say in this example that y is the outside function and u is the inside function? Yeah, that's exactly what's happening here. Y f of x is just the outside function, or f of u, which we're calling y here, is just the outside function, and the inside function is just g of x. In this first line, I know these two rules look different, but dy du, well, that's just, if y is f of u, that's just f prime of u, and then we're just plugging in u equals g of x, okay? Okay, any questions on that? Today is 100% an application of the chain rule, okay? So, here we go, implicit differentiation. So far we've only talked about differentiating functions that are explicitly a function of the independent variable, right? We've only discussed things like if y is x to the fifth minus 3x to the 1/2, then the derivative of y with respect to x, well, we can just use the power rule. 5x to the fourth minus 3/2 x to the minus 1/2. If y is t times the square root of 1 minus t squared, then the derivative of y with respect to t is that guy, and so on. Okay, so these are explicit functions of an independent variable. But then in math, there are a lot of times where we'll have a function that's implicitly defined. Okay, so for instance, in a circle, with a circle, the equation of a circle, we have x squared plus y squared equals 1, right? Hopefully we've all seen this equation defining a circle. Well, if I wanted to, I could rewrite this as an explicit function of x. I could write it as, well, I could move x squared over, I get y squared equals 1 minus x squared, and then y is equal to plus or minus the square root of 1 minus x squared. So the issue with this is that with the plus or minus, this isn't a single function. So to describe a circle with explicit functions, you need at least two. You need at least two functions to describe a circle, where with this single equation here, we're able to describe it just in one equation. Okay, so there are definitely times where implicitly defined functions are nicer to work with because I don't have to work with the plus or minus square root here. Okay, so we want to know, I mean, this equation just defines a curve, right? And the derivative then tells us the slope of that curve, the general slope. It would be nice if we could work with this instead of working with two different functions at once. Okay? This is what implicit differentiation is going to do for us. It's going to let us work with functions that are implicitly defined, not explicitly defined. So, and the way we're going to do this is with the chain rule, okay? So this is not new technically. It is new. But all we're doing is applying the chain rule to some specific things. Okay? So we'll illustrate with an example we've seen before. So first, if y is equal to 1 over x, which this is just x to the minus 1, then dy dx is what? This should be old hat. You guys know this. There's no funny business here. What's the derivative of x to the minus 1 with respect to x? Negative 1 times x to the negative 2. Perfect. So negative 1 over x squared. So with what I'm about to show you, you're going to say, why would I ever do this? It's way easier to just use the power rule. Well, this example, you would never do this example this way. I'm showing you how this works with an easier example, okay? There are some problems where implicit differentiation is infinitely easier than trying to solve for y as a function of x and then going from there, okay? So with implicit differentiation, I'm going to rewrite this function in a new, interesting way. If y is equal to 1 over x, then that means x times y is equal to 1, right? So this equation here implicitly defines y as a function of x. I mean, obviously, we got it here from an explicit function of x, right? So this implicitly defines y as a function of x. And so the whole idea here now is I'm going to differentiate both sides of this equation here. Differentiate both sides with respect to, if I ever write WRT, that means with respect to x. Okay, so we're going to differentiate both sides of this with respect to x, and keep in mind that y is a function of x. Okay, so we'll do the easy side first. So we're differentiating x, y. I'm doing d dx to both sides of this. Okay, so to go from here to here, all I've done is I've applied the derivative to both sides. Okay, so we'll do the easy side first. What's the derivative with respect to x of 1?
Zero.
Just 0, right? The derivative of a constant is 0. 0. All right, so now to make this even more explicit, well, no, I won't do that. So now on the left, I'm taking the derivative with respect to x of x times y. And y is a function of x. Okay? So what rule do I need to differentiate this? Derivative of x times y. I need the product rule, right? So here we go, the product rule. So the product rule says I'll take the derivative of the first thing, x. What's the derivative of x with respect to x? Just 1, right? So derivative of the first thing, 1 times, I'll leave the second thing alone. Plus, and this is where people get tripped up. So pay attention. Plus, now I'll leave the first thing alone. And I'll take the derivative of y with respect to x. But the derivative of y with respect to x is just dy dx, right? That's what we've been calling that this whole time, or y prime, whatever, however you want to write it. You could also write y prime here. That would be fine. But this whole thing here now is the derivative of the left-hand side. So I wanted to find dy dx. So now I just need to get this by itself, right? So how do I do that? Well, this y needs to move over here. I'm going to get x dy dx is equal to negative y. And then I'll divide both sides by x, right? Dx, or sorry, dy dx. Dy dx is equal to negative y over x. Negative y over x. Okay. Perfect. So this is technically, and most implicit differentiation problems will just stop here. However, we can actually go a little further because I know x times y is 1, so that y is 1 over x. And I'm just doing this to show you that we get the same answer. It would be pretty stupid if we got a different answer here. We should get the same answer for dy dx. So if y is 1 over x, well then negative y over x is just negative 1 over x squared, right? Which is exactly what we got before when we used the power rule. So are there any questions about implicit differentiation? This is one of the easiest examples you're ever going to see, but nothing really is ever going to change from what we did in this example. You're always going to be given a big equation with both x's and y's, and they're going to be all tied up. Like, you're not going to be able to solve for y most of the time. But that's fine. Just apply the derivative to both sides, and then you're going to solve for dy dx. And dy dx will always be pretty simple to solve for, relatively.
In the final example, and the final answer you showed, why is the x squared now?
Yeah, because so y is 1 over x. So when I plug that in here, I'm going to get, well, negative y over x. This is negative 1 over x all over x. And so this in the bottom here is over x over 1, right? So you flip the bottom and multiply.
Gotcha.
Good question. Any other questions on this? Is anything unclear at any step? All right. I personally feel like the best way to get comfortable with implicit differentiation is to look at a ton of examples. Okay. So first, the general strategy for implicit differentiation. So suppose that y is an implicit function of x, or really it can be, I mean, it doesn't have to be an x. There's nothing special about x or y. But if you have some equation involving two variables, one is defined implicitly by the other. Okay. So to find dy dx, you do the following. First, you take the derivative of both sides of the equation you're looking at with respect to x. And when you do that, you remember that y is a function of x. I covered that up a little. You remember that y is a function of x when taking the derivative. Okay? That's very important to remember. Step 2, then you're going to, the rest of these problems is always just algebra. It could be kind of complicated algebra, but it's always just algebra, okay? So from there, after you take the derivative of both sides of an equation with respect to x, then you're going to move everything around until you have all of your dy dx's, or y primes, whatever you want to write, until you have all of those on one side of the equation. And once you do that, you're going to be able to factor out that derivative, the dy dx. You're going to be able to factor that out and isolate it by dividing both sides by whatever you factored dy dx out of. Okay. So really 3 steps here in every implicit differentiation problem. All right, so let's look at some concrete examples, okay? So number 1, we're looking at the equation of a circle, right? So I want to find dy dx, which is going to tell me the slope of the tangent line to the circle at any point on the circle, right? So number 1. I want to find dy dx, x squared plus y is equal to 25. So what's step 1? What should I do to both sides of this? Take the derivative with respect to x, right? So I'm going to do dx right there, and dx 25. Let's do the easy side first. What's the derivative of 25 with respect to x? 0. This is going to happen a lot. You're going to have a lot of stuff with x's and y's is equal to some constant number. And so a lot of the time, not all of the time, a lot of the time, the derivative of one of the sides of the equation is just going to be 0. Okay? Now, the derivative with respect to x of x squared plus y squared. Ooh, careful. I gotcha here. We got 2x. I agree. But now y squared. So think of it as y is a function of x. So this is really like f of x squared, right? So if I want to take the derivative with respect to x of f of x squared, I need to use the chain rule there, right? So with this looking at this, what is the outside function? Or the inside function, whichever. The outside function, if I cover up the inside, so cover that up with a pentagon. That's stupid. I'm not going to do that. Get out of here. Get out of here, pentagon. If I cover up the inside, then if I'm taking the derivative of something squared, well, how do you do that? What's the derivative of just x squared? 2x, right. So I'm going to get the derivative here is 2 times, so that was the derivative of the outside. I need to plug in the inside. 1 second. Okay, that's no one. So there's the derivative of the outside at the inside, and then what do I need to multiply by? The derivative of the inside, exactly, and that's just f prime. And this is what trips people up, is like the derivative of the inside is just the derivative of the inside here, right? It's kind of a general thing. I'm just writing f prime, but that's fine. That's exactly what we need to find here. We're trying to find, if I replace f of x with y, then this reads just 2 times y times dy dx. Okay. So when we do implicit differentiation, you're almost always, when you're differentiating something with a y, you're almost always going to have to use the chain rule. Okay, so I'm going to get 2y, I agree, but then I need to multiply by the derivative of the inside, because y is a function of x. So 2y dy dx. Okay, is it clear to everybody where that dy dx comes from? Okay, yeah, so let's look more closely. If I just am taking the derivative, let's just look at the derivative with respect to x of y squared, where y is equal to some function of x, right? Well, this isn't just an x, so it's not just 2y, right? If this was an x squared, then yes, then it's just 2x. But this is really y is equal to some function of x, right? So we need the chain rule here, okay? So the chain rule says, well, first do pretend that that's just an x, and the outside function is x squared, and you will just get 2 times y for that. Oops. But then the chain rule says, then you need to multiply by the derivative of the inside, right? And the derivative of the inside is just dy dx. The inside function is just y itself. So if you want, you could also write f prime, or y prime. But that's where this is coming from, is because the inside, if this was just an x, then yes, 2x. But because it's the derivative of a function of x, we get 2 times the function times its derivative. Okay? All right, perfect. And so that's the big step. That's the calculus step in implicit differentiation, is the first step of differentiating both sides. And then the rest is just solving for dy dx. Okay? So what's the first step in solving for dy dx here? Yeah, you just need to get it by itself, right? So I'm going to subtract 2x from both sides. Okay, and when I do that, I'm going to erase this stuff now. When I do that, I'm going to get 2y dy dx is equal to negative 2x. And then now this is being multiplied out in front of the dy dx, so I'm just going to divide both sides by that. Okay? So dy dx is equal to negative 2x divided by 2y. And so this is just negative x over y. Any questions on that? So notice in particular, this says the derivative is undefined when y is equal to 0, right? But that makes sense if you draw the circle really quick. This was a circle of radius 5, x squared plus y squared equals 25. Circle radius 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. Beautiful. So when y is 0, here and here, that's precisely when the circle has a vertical tangent line, right? And a vertical line, we say the slope there is undefined, right? So the fact that the derivative is undefined when y is 0 actually jives with what we would expect to see. Okay. Any questions on this? All right, let's look at example number 2. Cosine of x times y is equal to 1/2. Cosine of x, oops. Cosine of xy is equal to 1/2. All right, and I'm trying to find dy dx here. So again, this is implicit differentiation. So the very first step every time is what? Take the derivative of both sides. Perfect. That's always implicit differentiation, always step 1. So I take the derivative with respect to x of both sides, d dx, cosine of xy. That's definitely going to be a chain rule problem on the left. D dx on the right-hand side. All right, again, we'll do the easy side first. So what's the derivative of 1/2 with respect to x? 0, perfect. What's the derivative of cosine of x times y with respect to x? So careful, this is actually going to require chain rule and then product rule inside the chain rule, and then technically another chain rule inside the product rule. Okay, so, but it's not too bad. So cosine of something, let's just cover up the inside first. What's the derivative of cosine of anything? Negative sine, perfect. So I'm going to get negative sine at the inside. So I'll uncover the inside now. And then times the derivative of the inside, right? So now I need the derivative of x times y with respect to x. So how am I going to take that derivative? Chain rule, but also product rule, x times y. Perfect. So product rule says I'll take the derivative of the first one with respect to x. Well, the derivative of x with respect to x is just 1. And then I'll leave the second function alone, so y. Plus, then I'll leave the first function alone, x, and I'll take the derivative of y with respect to x. But again, that's just dy dx, right? And we're done with the derivative of the left-hand side. Okay. Are there any questions about where this came from? Okay, so now I need to get dy dx by itself, right? So in order to do that, I'm going to need to do what?
Add sine of xy to the other side.
Be careful. This is, if I add, this is being multiplied by everything out here. So if I add it over, I'm actually adding this whole thing over because it's being multiplied.
You need to divide by negative sine of xy.
Yes. One thing I'm going to mention here to be careful about, though, is what if sine of x times y is 0? That would be division by 0, right? So we need to be careful. We can't do that when sine of x times y is 0. So actually, something that might be a little better to do, we're still going to have to divide by sine of x times y, but this will make it more explicit that when division by 0 is not okay. So first I'm going to distribute this negative y. Again, this is not really necessary. We could just divide by sine of x times y and make the caveat. That's actually what we're going to do instead. So divide both sides by negative sine of x times y. And then whenever you divide by something with a variable, you need to note, bless you, you need to note that we can't have sine of x times y is 0, because division by 0 is undefined, okay? So then when we do that, though, we get y plus x dy dx is equal to 0 divided by sine of x times y is 0, right? And then from there, we're going to get negative y, subtract y from both sides. We're going to get x dy dx is negative y. And then that tells me that dy dx is equal to negative y over x. And you might say, this looks exactly like the derivative with respect to x when we looked at x times y equals 1. And to that I would say, well, no, because even though it looks the same, the y here is different, right? The y is implicitly defined as a function of x. And so that y is going to be different. They're going to look similar if I show you graphs of the two of these things. Yeah, here. If I show you graphs of the two of these things, so first we had x times y equals 1. Here's a graph of that. Here's a graph of a truly implicitly defined function. So we had sine of, or no, it was cosine, right? Sorry. Cosine of x times y is equal to 1/2. Here's cosine of x times y equals 1/2. Here's this crazy thing that we can work with now. Okay, we know the derivative. If I tell you what point I want the derivative at any of these points, you can find it just using implicit differentiation. Okay, so this clearly, very clearly opens up a world of a whole new world of things we can work with, which is pretty great. Okay. So are there any questions about this example? Okay, all right, so one more. 1, 2, 3. Actually, this one's, I'll work the last one out separately, but I want to move on to one where we're actually finding a tangent line. Okay, so I'll work out number 3 before I upload the notes to Canvas, okay? All right, so, but an example, find the equation of the tangent line to the graph described by the equation y cubed minus x cubed equals 7/2 times x times y at the point 1, 2. Okay. So I'm finding the slope. I have it drawn here. The slope of that line-ish right there. That's pretty good right there. Okay, so I'm finding that tangent line. So for a tangent line, I need what two things? Or really any line. I need a slope and a point on the line. And in this respect, implicit differentiation problems are actually even easier than before, because with an implicitly defined function, if we look back at the graph here of this implicitly defined function, I can't just give you an x value anymore. I have to give you an x and a y to tell you where on this weird thing you are, okay? So in that respect, like you don't really need to work out what is my y value if I'm just given an x value. I have to give you both x and y, okay? So you know right off the bat that your tangent line looks like y minus, well, you know the y value is 2. So y minus 2 is equal to m, which that's the whole point in this problem is finding the slope, times x minus 1, right? Cool. So, good question, Saba. I'll answer that after class. If we find the slope, then we're done, right? But what should be screaming in your brain when I say slope? Derivative, right? So I need the derivative, specifically the derivative of y with respect to x. Okay, so I need to find dy dx. Okay. So how am I going to do that? Yeah, perfect. I want the derivative. I should just take the derivative of both sides. Okay, so I'm going to do dy dx, dy dx. Oops, that's not right. I'm going to do d dx of, this was y cubed minus x cubed equals, I can't do something to one side and not the other, right? So this is equal to d dx of 7 over 2 times x times y. So this is the first time we're not going to have 0 on the right when we differentiate. All right, so let's take this derivative. So what's the derivative of y to the third with respect to x? That's so close. 3y. Okay, so if this was just an x, it would be 3x squared, right? So I'm going to get 3y squared, and then just times the derivative of the inside, so the dy dx. But that was a very, very excellent attempt. Perfect, minus 3x squared. There's the derivative of the left. Perfect. All right, and then the derivative of the right. Well, the 7/2 is just going to come along for the ride. And then what's the derivative with respect to x of x times y? Or how do I find it? The same thing that we did in the last problem, right? So product rule, I'm going to take the derivative of x with respect to x. That's just 1. And I'll leave y alone. Plus, then I'll leave x alone. And then the derivative of y with respect to x is dy dx. By the way, if you want to write for dy dx, y prime, it's less writing. I just like dy dx because it's a little more clear to me. But if you want to write y prime, that's also fine. Okay. So this, and this is why I wanted to get to this problem before we stopped. We have this function here, or we have this equation here that we want to solve for dy dx. We want to solve it we want to find it at a specific point, 1, 2. Okay, and so once you take the derivative with implicit differentiation problems, if you're finding the tangent line specifically at a point, I would go ahead and plug in 1, 2 here. It's going to make it a lot easier to solve for dy dx. You don't have to. You could find dy dx as just a big equation involving x's and y's. But yeah, it's going to be easier to plug in numbers first for specific problems. And also, this advice definitely depends on the context. If you're doing a problem where you're plugging in a ton of points, yeah, solve for dy dx first, and then you can plug in all your points after that. But if you're just finding the tangent line at one point and then you're forgetting about this problem forever, then plug in right after you take the derivative. Okay? So I'm going to plug in x is 1, y is 2. So when I do that, I'm going to get 3 times 2 squared. I'm not plugging in anything here. This is dy dx is what I'm solving for. So you don't plug anything into that. Times dy dx minus 3 times 1 squared. This is equal to 7 over 2 times y is 2 plus 1 times dy dx. Okay. So when you do that, then you get 3 times 4, well, that's 12 dy dx minus 3 is equal to, and I'm going to distribute this here and here, is equal to 7 plus 7 over 2 dy dx. Okay. And now we could just need to move some stuff around. Let me add a page. Let's get all the dy dx's on the left. So we have 12 dy dx, 12 dy dx, minus 7 halves dy dx. And then we'll get everything else on the right. So this is staying on the right, and I'm going to add 3. Okay, so 7 plus 3 is 10. All right, any questions on how I went from here? I know I did a lot of algebra steps at once. From here to here. Okay, so then on the left, well, you can factor out a dy dx. We both have a dy dx in common, right? So I'm going to get 12 minus 7 halves dy dx is equal to 10. And then 12 minus 7 halves, what is that? Or how would I find it? Because this is really 12 over 1, right? Perfect. 24 over 2 minus 7 over 2. 24 minus 7 over 2. Yes. So that tells me 17 over 2 dy dx is equal to 10. And then multiply both sides by 2 over 17 to finish the problem off. So then dy dx is equal to, well, times 2 over 17 times 2 over 17 gives me 20 over 17 for dy dx. Okay. So then I can come back. That is my slope at the point 1, 2. I plugged in 1, 2 to find this derivative, right? So I can come back here to the very beginning. I know m is 20 divided by 17, and you're done. You found your tangent line. Okay. So those are really the two big ways that you're going to use implicit differentiation. You're just going to find a slope of implicitly defined function in general, or if you're finding a tangent line, again, use implicit differentiation, and then immediately plug in the point right after you take the derivative. Okay, there's not much variation on these problems other than just giving you different equations. So if this looks complicated, I promise it's really not. Come to me with questions if you have them, and we'll work through a ton of these examples together. This is not going to be on the exam, implicit differentiation, by the way. So I will work out these last couple examples before I upload these notes to Canvas, and then tomorrow is going to be a review day. Okay. Well, tomorrow I'll go a little bit more over these examples and then review. Okay. All right, so if you don't have any questions, please wipe down your desks before you head out, and then I'll see everybody tomorrow. Thank you very
Thank you.
much.
Thank you.